Hello guys, in today's lesson, you're going to be looking at the derivation of linear and angular velocity. In our previous lesson, we derived linear and angular displacement. So today we're going to be looking at linear and angular velocity derivation. So how do we derive the two of them? Quickly, let's have an analysis. Now, this is a uniform circular motion, not only uniform, let's say horizontal also, using the format. Don't forget, these formulas we're deriving are basic formulas. These are not complex ones. We're going to derive all the very basic ones, which will help us derive the complex ones easily. So how do we derive this? Now, this one we have here, this is a circle here. We have radius, don't forget. Now, at this very point in time, at point A and then at point B, at point A, this body moves with this speed. Then at point B, this body moves with this speed. Now, don't forget something. When we discuss the uniform circular motion, it is said that for uniform circular motion, although the speed is constant, we're not discussing speed here. We talk about speed. Speed is just the distance all around. We're not talking about speed. We're talking about vector quantities here. So we're talking about two things. First of all, velocity, which is this linear velocity, and also we're talking about angular velocity or centripetal velocity. So as you can see, the major differences between them, or one of the major differences, this one mainly cares about the movement of the body about an axis. This one cares about the angular movement, the speed at which the body rotates. That's what this one cares about. That's what this one's all about. Why this one does not really care much about the speed at which the body rotates, it mainly cares about this, the speed or the velocity of this very body at every edge. Let me say at this very spot, at this very spot, the body is coming with this crazy speed, if not for a kind of force called centripetal force that keeps it going. So at the very spot also, the body is moving with this speed. Look at its faces like this, about to go out like this, where a force keeps it back in motion. That is that's linear speed or linear velocity. I mean, you talk about velocity, but this does not really care about the does not care about this does not really care about the speed of the body or the velocity of the body at different edges. It only cares about just the speed of the body in the circular format, the angular speed. So that's one of the major difference. And also one major thing is this two here, this at this point and also at this point, they are constant, but there's a change in direction. But we don't really have that here. We don't have that for angular distance. Just what we have. So let's simply derive the major formulas. So we have an angle here, which is mainly in radians. The angle is very, very tiny. And also is the same thing as the angular displacement. It's in an angular displacement. So first of all, um, we're going to be deriving the angular velocity. So what's angular velocity? Angular velocity is written as angular displacement over time taken. That's what it is. So angular velocity denoted by yes omega is angular displacement. Angular displacement is theta over time taken. Now theta is in radians, rad, time is in seconds. So angular displacement is always in rad per second. Now I can also have it in another format. Sometimes, well, mainly in rad actually. The reason why it's in rad is the angle is very, very small. So you can have it in revolution. You can also have it in degrees, either in revolution or in degrees. Don't forget what brings them all together. Circumference is 2 pi radians equal to 360 degrees equals to 1 revolution. So this is a convergent point. So in case you want to do your quick conversion between as among them, I mean. So that's that for angular velocity. So let's quickly derive the formula for linear velocity or tangential velocity. So how do we get the formula for how do we derive the formula for linear velocity? Don't forget the linear velocity, which is denoted by v, is a vector quantity. Don't forget it's also a vector quantity. They're both vector quantities. So the linear velocity is equals to that's a displacement linear displacement over time taken. So linear velocity is also linear displacement is distance, that's s over t. What's formula for s? S is don't forget s is our linear displacement. We got our linear displacement as the radius times the angular displacement. So what do we have? This radius is theta over time. So The linear velocity is, we have the radius out here. Theta over time, what we have right here, you can see that we're trying to draw a parallel. So the V is R times theta over time is omega. So the linear velocity is said as angular velocity times radius. We look at this as a kind of, we're trying to draw a pattern. For linear displacement is angular displacement times radius. For how do I call it? For linear velocity is angular velocity times radius. So it kind of parallels more or less like when you attach a radius to anything angular, you're going to get the linear or the tangential stuff. So that is that for linear and angular velocity. So we're trying to continue today's lesson at this very junction. The final resource, so please subscribe to this very channel, Attention Mosaic. Follow me also Revelation of on Facebook and share this lesson with others. See you in the next lesson. Thanks.